Hi, my name is Ellie Rudolph. This is a 15-minute presentation for final project CSCI E-89. My project using a deep learning model to make a weather classification prediction using outdoor images as the input. Then use the result of the prediction to send instruction to smart home system. Here is the code workflow. First, it download dataset from Kaggle and then split the dataset into train, validation, and test. And then the code will do some data augmentation like flipping, shearing to reduce overflipping and also add more variety to images. And then experiment with two model. One is pre-trained model, EfficientNet B0. The other one is custom model, and then check the performance of each model and save the model. That is part 1. The purpose of part 1 is to find model that with accuracy higher than 90% and to find which one is the best model. On part 2, I don't have to run the training again because I saved the data. I just have to load the best module. In this case, the best module is the model using pre-trained data efficient B80. So I use the live images from windy.com and feed it to the model, and then from this I have two functions that will return two output. One is the predicted weather classification and the second is the confidence. If the confidence below 90, it will not do anything, but if it's higher than 90, it will assign different instruction to smart home devices. Here is how the code look like. First, it import all the necessary library, and then upload the Kaggle API. In this case, I use Colab, so I upload my API key to Colab. If you use a local laptop, then you have to put this key the same directory as your code. Then I download multi-class weather dataset. Then I just review this newly downloaded data, and then I assign each file and label, and also I want to find out the distinct label. So in this case, I have 4 distinct label. I will use this information as the output for the model. So the output of the model should be 4. And then I split the data. The challenge I feel is that to make sure that each data set has a balanced class. So I use this option, stratify option, to make sure that each data set has a balanced class. And then I review the split data to make sure it makes sense. In this case, train is 90%, validate is 5%, and test is 5%. And I do some data augmentation. This is to increase number of images, but it's also to reduce the overfitting. Then I normalize the images to make sure the size is correct, the color is correct, and the mode is correct. And then I review this to make sure that all dataset has 4 classes. I do not want, let's say, one dataset only have 1 class. I want to make sure that each dataset is well distributed, has a well distributed classes, and in this case true. And then I review the images to make sure it makes sense, the label match the photos. And then I experiment with the first model. The first model is using pre-trained model EfficientNet B0. Then I use model optimization early stopping here. in this model it's always stop on epoch 20, but the second model is actually sometimes stop at epoch 10, sometimes 12, I guess depend on the images. That show that it stopped when it think it need to stop. And then I review the performance. In this case, the performance pretty good, more than 0.095. This is a summary. And then I test with unseen data using test data set. I only test 10 of images. Out of the 10, 9 of them correct, only 1 of them incorrect. So I'm done with the model 1. Then I experiment with model 2. Model 2 is the same because the output has, the prediction have 4 classes, so I have to put 4 here. And the activation is softmax because it's multi-class prediction. And then the same like before, it used early stopping. And then I review the performance. It doesn't look good, below 0.05. And here's a summary. And I want to visualize performance of the two models, so I visualize them. The first model seems to perform much better. And then I save the model. So I'm done with part 1. The part 1 purpose is find the best model, and the model needs to be higher than 90% accuracy. Now part 2 is that to use the best model, make prediction, and send instruction to smart home devices. So for this one, I create 2 functions. One is to process the input image to make sure match the model, and second, it's it make prediction and return the class name and the probability. And then there is a second function to send instruction to smart home devices. So if check if it's confidence higher than 90, it will check the weather classification and take necessary action. But if it's less than or 9, it will not do anything. In this example, it used Sprint because each smart home devices have different languages. So I don't know what language to use, so I just use Sprint, but in the reality it should be some kind of signal to send a smart home to take action here. So because I saved the model, I do not have to do the train again. I just have to load the best model, and then I start using it. And here is the demonstration how to use it. Just provide the URL as the input, and then this function will return the predicted class and the confidence, and the second function will send signal. And this is an example how the output look like. So in summary, this class actually use several techniques. First, it used the data partition technique. In the class, we separate them on the OS level by putting in the separate directory and so on. But I found out that it's easier to do it this way, and at the same time I can make sure the class is proportion. And then the second technique is data augmentation to reduce overfitting and also add more variety images. And another technique that I use is transfer learning using pre-trained model efficient at B0. And another technique is used on this project is early stopping, model fine tuning, and also save and load the model. And here is the demonstration how to use the code. Just have to provide the URL and then call the 2 function. From what I learned from this experiment is that always check if there is pre-trained model available. The pre-trained model performs so much better than the custom model, Even I put many layers and different technique to optimize the custom layer, the custom model, the retrained models still perform better. And then the second thing is to make sure that each data set is well balanced. So in this case, I have 4 classes. I need to make sure each data set have 4 classes. I do not want that, let's say, the trained data only have one class, then the input will be biased. And also, despite doing extensive data augmentation, the models still do not do a good job at night due to lighting, especially when there are a lot of dust, uh, making appearance that it rained. It might need more images with that kind of situation. It doesn't seem like data augmentation is sufficient to address that situation. As I mentioned, the challenge is certain situation like lighting and dust, may snowflake and things like that may mislead the result. The second challenge is in this project I use windy.com. It allow people to upload images live using static URL. That works fine. The only thing is it needs constant internet access. In a remote area, this might not be a good solution. In a remote area, it might be necessary to have a URL available locally rather than through internet. That's all my presentation.